Hello, so in this video, we're going to start to look at this thing called the Ito integral. And this Ito integral is all about kind of trying to integrate stochastic processes. So basically what our aim is that we're going to end up with a stochastic process. Okay, so the integral from 0 to t, say for example. So those are our limits. We're moving from, if you like, we're moving through time, okay, and we've got a stochastic process which kind of changes through time. So if you like a value, so we go from 0 through to some time interval t. Okay, we've got some stochastic process going on that kind of models this interval from 0 to t. Okay, and we call that stochastic process x. Well, it's going to be x with respect to t. Okay. Thing is, this should be with respect to t, okay? But the thing is, what we do is we introduce a dummy variable. The reason why we introduce a dummy variable, so what I'm basically saying is we just replace this t with an s, and this t with an s down here. The reason why we introduce what's known as a dummy variable, this is what's known as dummy variable, okay? Dummy variable. The reason why, what a dummy variable basically is it's just there to stop us getting confused with this upper limit of integration, okay? This limit of integration is there of t. So basically, we've got an upper limit of integration involving t. So if we left this as t, then when we sub this back in and left this as t, when we sub this back in, there's always a risk that we may well get confused. We may get confused, okay? So what we basically do is we introduce a new variable to stop us getting confused. Right, so just say, right, this is S. It's a bit like having two Johns in a class, okay? If you're in school and you've got two Johns in a class, okay, then it can get confusing which one you're dealing with, okay? And you might get the two muddled up, all right? So you might, for example, call one of them Johnny or call them something else by some nickname, right? You leave one of them alone. So here's what we're doing here. We're just leaving this T alone and we're just calling this T just something ever so slightly different, and we're calling it S. Okay, they're still the same thing, okay? This is still time. This is still time, but we're just calling it S instead of T, all right? And it's what's known as a dummy variable. And this is quite a common technique which is used, but I think it's so common that not a lot of lecturers actually take time and take care to explain it. Because obviously if you've seen it for the first time, you're thinking, hang on a minute, that's supposed to be T. Why is it now S? All right, but that's all it basically is. We're just simply introducing a new variable to stop us getting confused with this upper limit of integration. Okay, and notice as well that the stochastic process that it's following is a Brownian motion, so it's a BS. Okay, so let's just take what we basically want to do is we want to try and give meaning to this integral. That's what we're trying to aiming to do. Give meaning to this integral, because if we can give meaning to the integration and kind of get the integration into our heads, then if you remember, with my last video when I was trying to kind of show you what's happening, what we're going to try and do, we're going to start with the integration, then we're going to go back to the differentiation. So we're going to start with the integration, then we're going to try and so we're going to try and give meaning to the integration, and then we can hopefully give meaning to the differentiation. Okay, so that's all to do with calculus, okay, stochastic calculus. So basically our aim is that we're going to try and give meaning to this integration, okay, and then hopefully if we can give meaning to this integration, then we can give meaning to the differentiation. Okay, so first things first, I'm going to give you a very kind of simple example. It's what's known as a deterministic function. So basically what I'm going to do is I'm going to take my stochastic process. By the way, I don't think I may have mentioned this. This XS, the reason why this is no longer just ordinary calculus, this is now stochastic calculus, is because this here, this XS, is a bit like a random variable. All right, well, it is a random variable. It's a stochastic process. Okay, and this stochastic process, so in other words, this, as I'm travelling along this curve, or this curve, this Brownian motion, I suppose, that is my stochastic process. Okay, the stochastic process is what is given by when I'm travelling along this curve. So what basically I'm going to do is I'm just going to take xs to be some constant function. I'm going to take xs to be k. Okay, so therefore what I'm left with is the integration over my time interval. So from the start of my time interval to t. Okay, so from here to here of xs. With respect to the Brownian motion dbs. Okay, I'm now just going to replace my xs with k. So I'm going to replace this k there. Well, what I can do is, because this is a k, just like with ordinary calculus, okay, then basically stochastic calculus kind of works in the same way as ordinary calculus. It follows very, very similar rules. It's just now we're looking at how we're going to deal with stochastic processes rather than just variables or functions. Okay, so what we're going to do is this is a constant, so I'm going to take this constant out the front. Okay, and I'm just left with 1 in here. So because it's a constant, it's not going to affect the integration at all. The reason why it doesn't affect the integration, okay, if you've got a function that looks like this, okay, you want to find the area, you know, say from there to there, you want to find the area under that curve, okay, well, just having a constant there is just going to stretch the area by, you know, a factor of k. It's going to stretch the whole function by just a factor of k, by some factor of k. No idea what that is, it's just going to be a factor of k. So it's going to stretch the whole function of a factor of k, well, then it's also going to stretch the area as well. So it's not actually going to affect, you know, the integration at all. Just as long as we multiply by k at the end, it's absolutely fine. So therefore, I can just consider the integration over the unstretched function and then just multiply it by k, then that's absolutely fine. Okay, so the area underneath the unstretched function. So I can stretch, let me just try and show you properly. Say if I've got a function that looks like that, okay, a function looks like that, and I find that area, and then I stretch it by some factor of k, so in other words, I make it a bit longer, okay, and then I end up with that, okay. Well, that area is just going to be stretched as well, okay, so what I can do is I can just find the area under this function and then just multiply it by k, because I'm still going to get the same thing. Hopefully I've made that clear. Okay, so basically what's the integration of this? Well, this is going to be, you know, it's going to be k times the integration of 1 with respect to bs, so I'll just have bs in here, okay, because the integration of 1 with respect to bs is just going to be bs, and my interval is going from 0 to t. Alright, so this is going to become k lots of bt, so sub bt in there, minus b0. So what have we got? b0. Okay, k lots of bt minus b0. Okay, well that is going to be, because we could just consider standard Brownian motion, this is just standard Brownian motion, so therefore that's going to be 0. We basically say that for standard Brownian motion, right, for standard Brownian motion we always start at 0. Sorry, that's not Brownian motion. We always start at 0. Okay, so for b0, so the Brownian motion at time 0 is just 0. Okay, so yeah, that's all that's going on. So we just let that equal 0. So therefore this is just equal to kbt. So in other words, we can say that that, you know, that should just be kbt. So that's kind of a simple example. And we can deduce from that example then that you know, so that's kind of a nice simple example to get sort of our, you know, our brains in gear, kind of build up a little bit of intuition. Perhaps it's sort of a slightly simplistic example if you're, but the thing is, what I'm trying to show you is how it, you know, start from basics now. We're going right back to basics because we're looking at no longer just a variable or function. We're now looking at stochastic process, so we need to be thorough. Okay, so we're going to looking at that. Nothing unexpected happens. Nothing unexpected happens. Oops. Nothing unexpected happens. Okay, we should expect that. But from this example, we can now move on to a slightly more complicated example. So say, for example, if we have a step function. So this is, say, for example, a step function. Now, what's a step function? Well, it looks something like this. Okay, it looks something like this. So basically, here we go. So this is going from A to B, say. This is a step function, right? It's just literally like a steps. There we go. Something like that. And then something like that. Oops. So this is a step function. Okay, this is a step function now. So in other words, each, you know, it's a function which consists of a series of steps. Okay, so if we try and now integrate it for over our interval, so from a to b, okay, so from a to b of our step function with respect to the Brownian motion, okay, because we tend to use Brownian motion when we're integrating stochastic processes. Okay, well then all this is it's just the area under each step. So it's just that area plus that area plus that area. Yeah, plus that area, plus that area. So it's just basically the area under each step. So in other words, what we can say is that if we kind of split this up into intervals, like from here, so this A, you know, this interval from A to B up into kind of intervals, so say from there to there, from there to there, there to there, there to there, and there to there. If we split it up into intervals, then all we can say that this is just basically the sum from, say, the first interval through to the nth interval, so let's call a counter I, okay, of each one of these going from A to B, where we just have some constant value, because you can clearly see that for each step we're going to have a constant value. It's going to have a constant value, so we're just going to call that constant value, say, ki. So this will be constant 1, this will be constant 2, constant 3, constant 4, constant 5, okay, and we're going from I from 1 to, well, 5 in this example, of our function, which is just going to be ki, because our function is a step function, which is this here, okay? And at each point, so if we divide it up into lots and lots of intervals, and we just basically say it's the area underneath that interval, so that k1, okay, that's that first step. Our second step is k2, so it's the area under that step, and the area is given by integration, by the way, yeah? Integration gives us the area, plus the area underneath K3, plus the area underneath K4, plus the area underneath K5. And that's going to give us the area under the whole function. The area under the whole function. So this is just all this is equal to. That's basically the whole idea behind there. Okay, and I've shown you what that thing is, what this thing is up above, you know, so it's going to be it's still going to be the sum from I equals 1 to n, but I've shown you it up here. So basically this, you know, when we had k in here, I've shown you from 0 to t, it's just going to be this thing. So it's going to be the Brownian motion from bt to b0. So in this case, it's going to be, so I'm just considering this integral now, it's going to be k, if I just stick a k outside, so ki, lots of the Brownian motion from bb minus ba. Okay, so it's just going to be the Brownian motion between those two points. Okay, notice that we don't go from 0 to t very deliberately, and we call it a to b rather than from 0 to t, because we say that Brownian motion at 0 should be 0. Well, the function value at that point isn't 0; it has some value. Okay, which is why I've gone from b to a, not from a to b. Okay, so that's basically what it is. So it's basically the Brownian motion. Now, basically, what I'm saying here in both of these examples, that here, you know, this is kbt. So basically, I'm saying that the integral of a stochastic process, so an integral of a random variable stochastic process, okay, and here as well, is going to be based on bt. Well, remember that you know, Brownian motion is distributed via a normal distribution. Okay, and if it's standard, it's going to be 0 times by, you know, it's going to be some constant, say, some constant times by, you know, my time intervals, so say from t to 0, or in this case from b to a, Okay, but it's basically, you know, it's going to be times my time interval. So let's just call it delta t, so my interval, okay, times my constant. Okay, and that's all it is. So basically what I'm saying, the most important thing that I want to get out of this is that the integral of a stochastic process, so stochastic process, if it's a deterministic function, is going to in itself be a you know, the answer is going to have a distribution. So when I integrate a stochastic process by stochastic calculus, okay, basically I'll get an answer out which has a distribution, and it's normally a distribution itself. It's normally a Brownian motion distribution. So B is normally distributed by, if it's standard, 0 k squared times my time interval, t minus 0. Okay, so something like that. Okay, so hopefully I've built up a little bit of kind of intuition now. You know, we haven't actually, I suppose, really looked at anything that we can properly use yet, but I'm just basically trying to build up a little bit of intuition. And in actual fact, you know, so I've looked at the case when we've got the integral of a constant. You know, if our random, you know, a random variable, a stochastic process is a constant, okay, but most of the time it isn't a constant. So let's suppose our random variable is just given by some reasonably well behaved function. Okay, well, if it's given by some reasonably well behaved function, so in other words, what I'm talking about is it's a function that we can kind of differentiate. It's a function that we can kind of differentiate. So maybe if I just draw something like that, then basically we can borrow ideas that are from the construction of the Riemann integral, which is basically just kind of what you're used to with integration. So basically, if we wanted to find the area under a curve, you know, that's the integral. That's kind of what's giving integration. Okay, what we basically do, so say if this is from, let's call it A to B again. So say if we're going from A to B, if we want to find the area underneath this curve, what we basically do is we split it up. We split it up into rectangles. Okay, we split it up into rectangles. So lots of little rectangles, something like that. Okay, something like that. Okay, let's go a little bit higher for the next one, something like that. So lots of little rectangles. Let's perhaps go a little bit higher like that. There we go, something like that. So basically what we're trying to do is approximate the function using rectangles, okay? And then what we basically do is we find the area of each rectangle. We find the area of each rectangle. Okay, we find the area of each rectangle, something like that. Something like that. So what is the area of each rectangle? Well, the area of each rectangle will be given by this width. So let's call it the area of each width. So let's call it dt. So some change in time. All this d just means some change. Okay, times by the function, the value function, because it's basically, if you find the area of a rectangle, the area of a rectangle, okay, this width here, I've just said is equal to dt. It's just going to be some width. But what's the height of that? Well, we're going from the 0 axis, or the x, the x-axis, whatever the axis is, to some value up here. So what will it be? It will be the value of the function at that point. So it'll be some value of the function, or let's call it t, yeah? Some value of the function there. Okay, so it'll be the value of the function times that, and that'll be the area of that rectangle. And then what we're basically going to do, this rectangle here, or this rectangle here, and this rectangle here. So basically we'll have lots of little areas, and what we want to basically do is we want to find the area of the whole function, and we're going to find that by adding them all together. So in other words, we're going to add them all together. Okay, and we're going to go from A to B. Okay, now the idea is, maybe if I don't call it little delta for the moment, let's call it capital delta. So I'm changed by moving some by some distance. The idea is that obviously you can see, say, especially if you take this rectangle, for example, you're higher than the function. Yeah, you've got this kind of thing going on. So you've got the rectangle going on. Let's get rid of that. Da-da-da-da. You've got the rectangle going on, and as you can see, it's just an approximation. So let's say, for example, let's draw it a little bit better. Okay, it's just an approximation. So obviously it doesn't actually hit. We've got this kind of extra spare space. So it's not the actual area underneath the curve. So basically the idea is that we take a smaller and smaller width of the rectangle until eventually we end up with such a narrow strip that it actually gives a really, really good approximation for that little strip, for that area underneath the curve. Okay, so basically what we do is we basically make delta t, go to 0. In other words, this is going to become little delta t. So we're considering such a small little change. There is a change there. It's not 0. There is a change there, but it's such a small change that we don't call it capital delta anymore. Capital delta denotes a big change. Little delta denotes a little change. We're now denoting a tiny change. A tiny change that's so basically, it's basically 0. And that's tiny little change we call dt. So now what we're doing is we're changing it to dt. Okay, and what we're basically doing is we're taking the limiting sum. Okay, we take the limiting sum, so we actually show that we're taking such a small, we're adding such small areas together that we call it, just s, but we call it by an elongated s. So it's s for sum, just like sigma is the Greek letter s for sum. Okay, but it's no longer a big change, it's now a tiny little change. To show it's a tiny little change, we show it's an elongated tiny little s. Okay, so we call it an elongated tiny little s. Okay, and that's your kind of familiar integral that you're used to. Okay, so that was a very, very quick kind of summary of what the Riemann integral is. Well, now we can borrow ideas. So say, for example, if our random variable, okay, say if that random variable could be approximated by some curve, okay, then we can use these ideas that we've just talked about in the Riemann integral. So in other words, what I'm talking about is that, say, for example, if we have the integration of our random variable, which is just given by some well-behaved function, and again, we will have Brownian motion going on. Okay, well that is just going to be equal to, or rather it's not going to be equal to, it's going to, as we consider smaller and smaller time steps, like we did sort of above, when we talked about above, we basically take the limiting sum, so we're taking smaller and smaller time steps. So in other words, the integral of this stochastic process is going to basically become just exactly what we had here, So what will it be? It will just be the integration, again, over the same interval. The interval doesn't change, okay, over just our standard integral, our standard Riemann integral. Okay, so instead of t now, I'm just using s, just because I want to. Okay, so in other words, as we take smaller and smaller time steps of this stochastic process, so say, for example, we've got a stochastic process going on, okay, and we take smaller and smaller time steps, then basically, providing that say, for example, if f of s was some well-behaved function, essentially what we're doing is we can basically just consider this thing, because it's some well-behaved function already, we can just consider it just using ordinary calculus. So something like that, okay? And if we wanted to, I've said that, when we find the integral, I've said up here, said that when we find the integral of a stochastic process, we basically should get some distribution. What is the distribution of this thing? So what is the distribution of this thing? Well, it's going to be a normal distribution with mean 0 and variant. Well, how much does the function vary by? If I just draw it out like this, got this function going on. Okay, so this is f of s, okay, from A to B, okay. How much does it vary by? Well, it varies by the area underneath this curve, doesn't it? It varies by the area underneath this curve, which I've just said is going to be given by the area underneath this curve, f of s ds, but that's what the standard deviation is. But I'm talking about variance now, so it's just going to be this squared. It's just going to be this function. Maybe if I write that a little bit better. Come on. There we go. This function squared. Okay, because the standard deviation will be the area underneath this curve. Oh. The standard deviation will be the area underneath this curve, right? So the variance is just the square of the standard deviation. Remember, the standard deviation is just like, if you like, steps above and below the mean. If you think of it, I always think of it like a normal distribution. Okay, so a standard normal distribution. So this is, say, that, well, this doesn't even have to be standard, does it? Come on. Okay, so I always think of it as we just have a normal distribution. Okay, this is the mean. Okay, and standard deviation is how many steps above and below the mean they are. Okay, so the standard deviation is the steps. The variance is just how much it varies overall. Okay, so the variance overall is just the square. So variance is just the square of standard deviation. I think that's right. So sigma. Yeah, so variance is just going to be equal to the standard deviation squared. So that's why this is this function squared. So basically it varies by the area underneath this curve. You know, the function varies from, say, this axis to this, you know, to whatever this curve is. The function varies from this axis here to this curve by the area. Okay, so that's why it's given like that. Okay, which is fine. So again, you know, I'm just building up your intuition for you. But remember, so we've dealt with the case when we've got x of s is just going to be equal to some constant, and also when x of s is so a random variable is a constant, when random variable is some simple function like a step function. Okay, and we just showed that we consider that step function just as constants. Okay, and then we consider our random variable as a slightly more complicated function, but still well behaved, kind of, you know, more familiar function that we're used to dealing with. Okay, and now what we need to do is we now need to consider x of s to be a random variable, so it's not any of those things. So let's consider the case when it's not any of those things, and that's what we're going to do in the next video.